because I know it takes a minute or so. Hello. Getting over the technical difficulties.
You got that on mute, right?
Yes.
Getting over the technical difficulties. It'd be on YouTube, wouldn't it, Shannon? There you are. Where's the chat? Can you see the chat? If you want, I can just use your phone. Just got to use your phone.
I don't know.
Can you see that?
There are 4 people on at the moment. We will get started here at a little after 5 o'clock just to make sure that we can handle any time delay. There's about a 10 to 15 second time delay from what I say to what I actually can hear.
Actually, the chat is instantaneous. 4 people on at the moment. We will get started here a little after 5 o'clock just to make sure that we can handle any time delay. There's about a 10 to 15 second time delay from what I say to what I actually hear.
If you are just tuning in new to us, I'll go through introductions. But if you're just tuning in new to us, this is Blackland Geology and Reptiles. We have collectively, my wife and I have been doing education for 25 years now. I have been teaching geology for 16 years. And over that time, I've taught probably 1,000 students. No, actually, probably in the several thousands of students. I teach earth science, I teach geology, I teach natural disasters, I've taught environmental science, and I've taught some upper level geology classes. If you have any questions at any point, put them in the chat and we will take a look at them, and I will pause to actually do that. If you see a time delay between what it sounds like I'm saying and what's on the screen, that's the difficulty of doing Zoom through YouTube Live. It's about a 10 to 15 second delay. And every once in a while, my wife will probably be in the background with a snack.
Oh, yeah.
So,
not a snack.
What's the time?
Huh? It is exactly 5 o'clock. Go.
So, I am Brett Burkett, the co-owner of Blackland Geology and Reptiles, and I figured that we would get started on this at 5 o'clock. Like I was mentioning before, my wife and I have about 25 years, maybe more than 25 years of geology teaching experience. We've taught environmental science, we've taught natural disasters. And the reason why I wanted to give a lecture on volcanoes is because this is what my specialty is. When I did undergrad was geology. When I did graduate school, you have to choose something much more specialized than just geology. So I wanted to do volcanoes, and my alma mater for graduate school was the State University of New York at Buffalo. And my specialty was studying explosive volcanic activity and specifically trying to develop safety protocols for people that live in disaster prone areas or areas that are right next to volcanoes. And so my goal through my research was to try and figure out ways that we could inform policymakers, et cetera, when something was dangerous, design hazard maps to know when to evacuate people or where to evacuate people, sort of the same kind of safe zones that you would look at for hurricanes, areas that would be flooded that way, tsunamis on the West Coast, et cetera. And over the last 15 years of teaching geology, I find that there are a lot of misconceptions about volcanoes. And part of that comes from popular media, of course, because we like the sensationalized movies. We like explosions in the background. We like the beautiful majesty that is lava flows or that are lava flows. And so I figured one of the things that I would do is I would address some of the misconceptions about that and give sort of an introduction to volcanoes if this is a new concept to you. I mean, we all know what volcanoes are, but the exact nuances of them. And I figured the best way to start would be using this picture right here. This is a picture of Mount Etna in Sicily, one of the most continuously active volcanoes on Earth. It has been active not all the time, but there has been recorded activity going back 3,500 years, and that's a pretty consistent amount of volcanic activity. The actual mechanism for that is remarkably complex, but we can just lump it under plate tectonics. There's something funky going on in Sicily in the Mediterranean. But the reason why I like this image is it shows a lot about what people think immediately about volcanic activity, and we can address some of those misconceptions here. For example, when you look at this picture, you see the classic rivers of lava, right? The lava is yellow because it's hot. As it starts cooling down, it becomes red, and then eventually it becomes black. So it goes from incandescent, glowing, to something which is still moving, but is cool enough that we do not see it in the visible spectrum. When you see this, you can actually see several behaviors here. You can see the dark spots where it appears like the lava has moved around obstacles because it does move around obstacles. In this case, the lava is affected by topography. It'll move into valleys and low spots. If there's a high object, it'll move around them. We use that term sort of like water, that it follows the path of least resistance. On the left side of this image, you can see what look more like explosions where material is coming out. It is glowing, it's incandescent, and it's coming out like cannonballs. And you can almost see that it follows these sort of curved trajectories, like something is being shot out and sailing and then hitting the ground. We can also see in the foreground 3 people. They're just seen as black shapes. The reason why I like this is because people go, oh, those people, they're dumb. Why are they standing there? They're in harm's way. Well, no, this particular type of volcanic eruption in general does not kill people because the lava is generally what we would call well behaved. And what does that mean? That means that it follows valleys and low spots. It has a speed which is not generally ridiculous, on average about 4 miles an hour, which is a walking pace. It generally doesn't surprise us, but it has, and it can. And what I tell my students is this: if you were to die from an eruption like this, you'd have to either be dumb or unlucky. And people have gotten injured and people have died from volcanic eruptions of this type. But this is not the kind of volcano which kills most people. But this is what most people think of because we get this sexy lava moving down. And in movies, we have a tendency when we see lava of this kind that people are wearing the giant metal suits. They look like the flexible aluminum suits. And that very rarely happens. We have done that in the past. One of the famous examples in recent memory is Jeff McElwee, who did Ambrim Volcano in Vanuatu. And you've probably seen this famous video of a guy in the what looks like the reflective suit standing at the edge of this boiling cauldron of lava. And that does occur. And that is a hazardous environment. But also, in that particular case, you can't just encounter that. That is on a remote island that you have to rappel down to. And it took Jeff Mackley about 6 months to really get those good images there because of the hostility of the environment around, just the atmosphere, etc. So that's the kind of picture that we typically see. So let's talk a little bit about what that is, what we are looking at, why it generally isn't harmful to people, how it can be harmful, and then what the really harmful stuff is. You may remember 2 years ago in Hawaii, we had evacuations because lava was moving toward people's homes. You've probably seen the famous video of a person who had put up a cattle gate and the lava pushed against the cattle gate and eventually broke the bindings that fastened the cattle gate. And it was this weird, blocky movement of black rock that was sort of like the blob or a tank tread moving across the landscape. And one of the other famous videos that came out of that was this white Mustang swallowed up by the lava. Now, that lava we can see on top is black. It is cooler. It's still remarkably hot, but on the bottom, it's this reddish color because it is remarkably hot. This type of lava we call basalt, B-A-S-A-L-T. Basalt is a remarkably iron and magnesium-rich lava that gives it its dark color. It erupts at a high temperature of about 1,000 to 1,100 Celsius, which is 2,000 to 2,400 Fahrenheit, somewhere in that range. So it's about 4 to 5 times as hot as your oven goes on the hottest that you can really get it. And I understand we do that logic where we go, okay, if you're going to make a pizza, you make the pizza at 400 degrees for half an hour, but let's just try and increase the temperature and it decreases the time. We know it doesn't work that way. This is really hot. But as you can see, that car is only catching on fire because of the proximity with the lava. And there was somebody that had to stay here. There's a video of this that had to stay from the vantage point of the camera, which wasn't that far away, and watched the lava eat the car effectively. The reason why I like videos like that is it shows that while this lava is incredibly hot, the person was, say, 30, 40 feet away, probably wearing a shirt and shorts and sandals, and they were watching this and it didn't kill them. And it wasn't one of these things that, oh no, surprise, it suddenly moved really fast and just overwhelmed the person. One of my favorite videos that came out of that was a mother that was driving away in a minivan, and I think it was her kid or a family member was videotaping lava erupting out of the street in the back. And it was one of the most relaxed evacuations because it's moving at about 30 miles an hour. The car is moving at about 30 miles an hour, and you can just see this blob-like lava come shooting out in the back. So what does that mean? That means, is there anything to worry about? Well, sure. Physical structures, things that are stationary like this car, they can be destroyed. But nobody died, as far as I can remember, nobody died in the 2018 eruption from Kilauea. Nobody died in that. The lava tends to be behaved following valleys and low spots. It can reach speeds of 4 miles an hour. But as long as people were able to evacuate, sure, they lost property, but they didn't lose their lives. The types of volcanoes that generally produce these, we call shield volcanoes. So if you look at the big island of Hawaii, it's made up of like 4 overlapping volcanoes that have periodically erupted at different times: Kilauea, Mauna Kea, Mauna Loa. And the general plan of those volcanoes, if you'd sort of step back and look at it from a big distance, we say is a shield volcano because it looks like a night shield. So we have this incredibly tall structure. There's snow on the top. It's 14,400 feet above sea level. And Mauna Kea is the tallest mountain on Earth. If you look at it from base to top, it's actually about 400 feet taller than Mount Everest, but most of it's underwater. But you can see how comically wide it is in comparison. And we say it looks like a night shield lying on its side. Well, how does this work? Because the lava that erupts has an easy time moving across the surface, so it tends to spread far and wide. And so what we get is a big volcano, sure, but one that is much wider than it is tall. I tell my students, it's like making pancakes. The batter can flow across the pan. When you turn it into the solid structure, you get a flat-ish wide and very narrow, or generally narrow, pancake. So how do I get a volcano like this? Lots of pancakes. This has just been erupting prodigious amounts of lava for the last 800,000 years, building up a structure from 4 different general centers and creating this big shield volcano. How do we then not need to worry about it? Because, like I said, the lava is well behaved. Have people gotten injured from it? Yes, but usually they get injured in ways they're either uh, cavalier. They assume because it generally can't hurt people that it just can hurt people, and they get too close. They get affected by products when the lava enters the ocean. If you remember 2 years ago, a boat was damaged, probably irreparably, because a giant chunk of lava went through the top of the boat. How did that happen? Because lava was entering the ocean, and you get these weird, we call them phreatomagmatic, the interactions between, or hydrovolcanic, water and hot magma. And blobs got shot into the air, and one of them went right through the top of the boat. And when they interviewed the people made this comment like, I don't know how this could have happened. Well, you sailed a boat next to lava that entered the ocean. George Ulrich in 1983 got into trouble. He was, as far as I understand the story, he was a scientist who was doing his research by himself on one part of Hawaii where they were having active lava flows. And he walked out onto what appeared to be solid lava that was cool enough for him to stand on, but like a thin skim of ice over a lake, he cracked through it and he went into the lava. And if you've watched a movie like Volcano, this causes somebody to dissolve Wicked Witch of the West style. They're like, I'm melting, and they disappear. That didn't happen to him. When he went in up to his groin, and he was rescued by other people that happened to be there. And he got third-degree burns over his legs, which he needed skin grafts and medical attention for. But the interesting thing is he didn't lose his legs, because the temperature difference between the lava and his legs was like ice to that lava. And so the lava cooled around his legs and effectively gave him lava pants. And because rock is a poor conductor of electricity, or a poor conductor of heat, then it somewhat protected him from further burns. You've probably seen a video where the Mythbusters did this. Can you dip your hand into molten lead? Don't do this. But they proved that if you had this sort of vapor barrier around your hand, that you would be somewhat protected from the molten lead. And the same kind of thing applied here. He had this sort of protective rock around his legs, and he survived. So where can we go from here? If we look at this sort of well-behaved lava, this lava, we say, has a low viscosity. And what does that mean? Most people use the term viscosity to mean thickness. They say how thick something is, but that's not really, that's a good vernacular, a simplistic vernacular expression. But what we say is how resistant it is to flow. So something that has a low viscosity has a low resistance to flow. And the visual that we have for that is water. When you spill water on a table, you immediately go, oh, pick up the papers. It's too late. Why? Because the water spreads flat across the surface. It forms a very thin surface, but it covers a huge area because it can travel with ease. So we don't like pour the water in the table and get a mound of water like Jello. It spreads across the tabletop. For this type of lava, what we call basalt, and you can see several pictures here of that basalt. Basalt has, for lava, a low viscosity. Now, it isn't the same viscosity of water. It's actually much more viscous than water, but we can see some evidence of low viscosity. How? Well, it sort of behaves like soup. If you've ever had soup on the stove, you get, if you haven't stirred it in a while, a thin skim, a skin of soup on top that is somewhat hard but deformable. What is that? And if you say, wait a minute, I don't know what soup you're making, watch it the next time you make soup. You'll get this a film on top, and that's because the soup toward the top is cooling off, and you're getting things that coagulate, and so you get this skin, and you can deform that with a spoon, stir it back in. But we can see some evidence of it here. Here, the lava is cooling from the top down, so it loses most heat from the surface. So that's why it is darker on top. And then the stuff underneath is kept liquid, continues to move, can flow across and form thin surfaces. How thin? Well, you can see from the no parking signs, that lava there must be a foot thick, foot and a half thick, maybe 2 feet, and that's multiple lava flows. It is thicker than water because you generally, unless the water's got something in it, you wouldn't see water making these weird folds, and water will not form surfaces like that, right? Unless it's frozen. So here we have some evidence that it can flow with ease. We get this sort of thin, skin like texture. And this is how sometimes people get into trouble, like I told you with the scientist that fell in. Well, if you notice, as the lava cools, we do not see that incandescence, it looks black. So if you were to encounter that, you might go, oh, now there's hard lava there. Well, it might not be, it might still be deformable. If that lava moves slightly faster, then like with water, we get turbulence with water. The faster water moves, we tend to get turbulence. Well, if the basalt moves faster up to that upper, sort of toward the upper end of that 4 miles an hour, say it's coming down a steep slope or something, the lava will actually experience turbulence, and that thin, sort of ropey skin on the surface will break up. And when it breaks up, what we get is this jagged pile of rock. And the reason why I like the image on the bottom half here, we can see this sort of like pasty blob moving across with black chunks on top and glowy bits below. So we still get that temperature cool at the top, hotter down below. But we can see a juxtaposition between the sort of ropey skin on soup below and this blob-like layer. And look at the picture in the upper right. The lava is hot from that distance. That man would absolutely know that that lava was hot, but he's not catching on fire. He's not wearing a giant metal suit. I've had friends that have gotten close. They're scientists. They got close and they took all the proper precautions, but they forgot to do things like put their hand over their eyebrows and it ignited their eyebrows. But they didn't catch on fire like a Roman candle. You'll see, because of this, you'll see videos that have popped up online, like somebody sticks a can of Campbell's Chef Boyardee soup into the lava, and you can watch as the soup is effectively cooked by the lava. But if you watch videos like that, the can doesn't instantaneously melt. And it shows how there is this awesomeness to it, this incredible heat coming out of the earth, this amazing video, this sexiness, but at the same time, it's not like we see in movies where it just incinerates the person and they dissolve. We can also get an incredible amount of gas that can build up, and if the gas builds up in that basalt, instead of it flowing across the surface, it will jet out like somebody shook a can of soda and pop the top. So when the images appear here on the screen, we're going to see 4 different images of what we call fire fountains. And a truer name has not been coined because we have jets of lava that are shooting up into the sky. This is, in each of these cases, 3 of them are from Hawaii and 1 of them is from an island in the nation of Iceland, the black and white one in the upper right-hand corner. We can see jets of lava shooting out, and this is due to gas. In a can of, say, Coca-Cola, the gas is kept dissolved in the liquid, and when you open the top, that causes a decrease in pressure, and the gas that was kept in the liquid under pressure wants to come out. And so those bubbles very quickly rise to the top. If you shake the can of soda, then more bubbles than would normally be exposed just to opening the top all rush out, and the bubbles rushing out and popping can throw a lot of soda into the air. If you've ever gotten a fountain drink, the same thing applies, right? When it hits the sides of the container, a lot of the gas that was kept dissolved comes out, and so it bubbles. And when it bubbles, the gas is very quickly depleted and it goes back to normal, right? To this sort of placid surface. The same thing holds true here. If we get a lot of pressure, a lot of gas building up under the surface, and then it experiences a crack that breaks the surface open, that gas will shoot the material up into the sky. And we go, well, that's not like the can of soda or the fountain drink. Well, yeah, it is. If you open the can of soda or the fountain drink and you put your hand over the top of the can or the glass, you'll get little bits of Coca-Cola that are hitting your skin. Now, in this case, this is just a larger version of that same concept, right? And this also shows the low viscosity nature of the basalt. So why does this occur? Gas bubbles are rising. They pop. As they pop, they throw little bits of coke, or in this case, they throw bits of lava into the sky. And the lava here can shoot up to a mile or maybe a mile and a half into the sky. The gas in Coca-Cola, carbon dioxide. The gas here, largely water vapor, and then carbon dioxide. And those two gases can make up 3 to 4% of what shot out. Now, we look at these. Don't be near those. As you can see, the Kenai helicopter pilot here flying close. Those people, amazing. Their skills, amazing. No, as a volcanologist, that's I'd rather be the one taking the image there. If you look at the black and white image in the upper right-hand corner, you can see also the temperature change. The lighter color in the center is hotter. The darker color to the edge is cooler. So we can start seeing how it cools off toward the edges because they're interacting with the atmosphere and cooling. Now, all of that, we would say that is generally well behaved. We understand the processes, the lava moves with ease in general. We don't generally need to worry about it as long as we are taking appropriate precautions. We're not being stupid, or hopefully we're not just being in the wrong place at the wrong time, being unlucky. The problem comes in when we change the actual chemistry of the lava, and what we end up getting is something which is fundamentally explosive. So this picture here, this is Mount Pinatubo from 1991. In the 20th century, it was actually the second largest historical eruption, but the first one affected few people in remote Alaska. This one was in the Philippines. And I think the death toll was somewhere around 3,000, 4,000. I'll have to check my numbers there. But when you look at something like this, it looks like a mushroom cloud, an atomic explosion. If you notice the color here, this is not dark colored. We don't see the reds, we don't see the blacks. We see a sort of light to maybe medium gray. And we get this cauliflower-like appearance to the cloud. I've superposed on here a little black line which shows what 1.5 miles of basalt would look like in comparison. So those jets that we just saw in the last slide, those were at most, none of those were, but they could be up to a mile, mile and a half in size. Well, in comparison, Mount Pinatubo was, I think, 23 miles into the sky. What causes that? We change a little bit. We don't change the gas, we change a little bit of the chemistry. And when we change that, then we get something which is much more viscous and it builds up much more pressure. So when the pressure is released, we get something that looks like this. The danger in this case isn't, well, I could stand nearby and take a picture and I know it's hot. No, because now we get particles that could come falling out like snow over a large region, making it hard to breathe. We could get a whole bunch of stuff, which we'll look at right around the volcano itself. We can get interactions which lead to condensation in the atmosphere, rain. So we get mud, we can get mud flows. There are a whole bunch more problems here. And I tell my students in these types of eruptions, the danger is being nearby, right? You need to have taken advance warning ahead of time. It's not just, oh, I can be cavalier and stay a safe distance. Don't be nearby. So let's go back and talk about viscosity a little bit. And this is where a lot of people get confused. We said water has a low viscosity. All of the lava that we could possibly talk about has a much higher viscosity than water. But in lava, we have the stuff which is runny and the stuff which isn't. And here's a good visual. Water spreads easily across the tabletop, low viscosity. Much higher viscosity, there's pudding. We'll assume that it's cold. That will spread and will relax over time, but much slower than water would, so it can hold its shape. Low viscosity, much higher viscosity. So why? Why does that occur? Well, this goes to a little bit of, I want to cover a little bit of the more detailed science, and then we'll get back to talking about why that's important. Viscosity comes in this way. If you look at that iron, magnesium rich, that dark colored runny stuff, inside that runny stuff, we have what is called a silicon oxygen tetrahedron. What is that? It's a pyramid, silicon in the center and the big four balls on the outer edge, that's oxygen. In the basalt, we have a liquid, and in that basalt are these little pyramids. As the liquid moves, those little pyramids will roll sort of like sand particles in water, like a stream. They somewhat restrict the motion of the liquid because the liquid then has to move those as it is moving, right? Move those as it's moving, sure, right? This is what happens when it's a Friday night. When it does that, it doesn't have much difficulty. I tell my students, this looks like the little boba in bubble tea. You get those weird tapioca pellets at the bottom. As you turn the glass, they move, right? The liquid doesn't really feel the effects of those, and we don't see it. It's not like I turn the glass and because of all those little dark colored balls that the liquid takes some time to slosh from one side to the other. But if I increase the amount of silicon, instead of me having little individual pyramids like those bubbles in bubble tea, right? They connect, and they connect in these chains, and these chains act like hair in a drain. As the liquid attempts to move, it has to then move those chains, and those chains are flexible. It has to move those chains in order to actually make the lava move. And this isn't exactly what's going on here, but this is a simplification, and it works. If I have gas, if I have gas, the gas can easily move around those little pyramids in basalt. So the gas doesn't build up much pressure. So when the top is opened, right, when the crack opens up, the gas can pretty much easily escape. In the case of more silicon, when I have these big chains, what really is going on is the gas needs to be able to become visible. It needs to grow. So that means it has to push the liquid aside. Well, the liquid has these little hairs in it. So it has to then work to try and push those aside. And that's difficult. So it has to build up so much more pressure before it can actually move them and have our eruptions. Right? We could think about, well, that's the easiest way to think about that. So what is the transition? Well, the transition is once I move away from that dark colored material to sort of a medium gray or a light gray, we are now into the explosive range. I have worked on 11 volcanoes over the years. I think 11 volcanoes, sure. I tell all my family and friends, I said, I have never watched a volcano erupt. I'm always there right before they erupt or right after they have erupted. And that's probably for the best because I'm accident prone. This particular volcano here, this is Reventador volcano in Ecuador. And I got to work this volcano. I did not take this picture. A friend of mine did, an acquaintance that I worked with did. But we can see we have this sort of mushroom-like explosion in the background. The people who are in, the person who took this image was safe distance, but from that, it doesn't look like they doesn't look like they could be. We can see the lighter color here. What's driving this? Gas, mostly water vapor, some carbon dioxide. Now, here's the weird thing. If you were to actually be able to zoom in there, we can see this from the particles that have been put out. We can see this from taking pictures of numerous volcanoes that have exploded like this. Right above the volcano itself, there is this area about half a mile to a mile in height where particles are just launched into the sky. So we get that launching effect from gas exploding. But once we get about a mile, maybe a mile and a half into the sky, eventually we run out of energy, like a shuttle launch that didn't have enough fuel. It'll rise into the sky and then it won't be able to rise any farther. The weird cauliflower-like nature is because we are shooting, or the volcano has shot material into the atmosphere. There's stuff in it. The atmosphere is full of gas, right? Water vapor, oxygen, nitrogen, etc. So as that material shoots into the sky, it shoots in with a lot of force, and then it starts mixing into the sky. And if you've ever taken, say, one of those flavor enhancers for your water and you've squirted into the water, if you watch the videos, when they first squirt it into the water, it comes out as a really narrow stream. But once it gets several inches into the water, it starts stirring. That's what this is doing right here. As it launches into the sky, it starts interacting with the atmosphere and stirring. And as it stirs, it's hot. And so as it hots, it heats up the atmosphere. And so gas starts rising up into the sky. and it will continue rising until it runs basically out of thermal energy. It's the same temperature stuff around it. And as it moves higher, it starts to mix even more and more. And so we get this cauliflower-like appearance. And you can see it causes these weird atmospheric effects. Not much clouds, but right around the volcano clouds. That particular eruption shut down the capital of Ecuador, Quito, for about 3 days. That we said it was a volcano that occurred without warning. That is not technically true, but basically accurate. It technically had a warning, but it occurred, and only after the fact could we look back and go, oh, it actually did warn us. So that's why it caught them off guard. The volcanoes that produce eruptions like that, we call stratovolcanoes. In this case, strato means layers. And the layers are explosions because we get gas. And then once the gas goes away, we get flat soda lava, right? So what we get is we get these explosions, particles fall out of the sky like snow, a whole bunch of other effects, and then this sort of thick, viscous lava. In this case, the lava does not travel very far, so we get a pile rather than this broad structure. And we say it is roughly equally wide and tall. It makes a cone. This is one of my favorite pictures. This is Mayon volcano in the Philippines, and it shows something about volcanoes. Sometimes volcanoes can steam without erupting. So what you see there, the white stuff coming out, is just water vapor. It's steam. In this case, there are cracks in the top, and some of the pressure from gas is being vented as steam. That doesn't mean that the volcanoes just go, well, I have a pressure release, therefore I can't erupt. No, it just means that some of the pressure is being released. It also shows some of the problems we have because we go, well, how do those people evacuate? Well, they live next to the ocean, boats. Well, the volcano, depending on the nature of the eruption from it, the products that come from the volcano, if they're shot up into the sky, sure, they might be able to evacuate via boats. But if the volcanic products, and we're going to talk about this in the next slide, if the volcanic products come down the volcano, they can reach speeds of 100 to potentially 150 miles an hour. And as this cloud of gas and rock comes down the volcano, they don't have enough time to get the boats out. And there have been stories where people have tried to escape with boats. Clouds catch them, burn the boat right down to the waterline. I realize I get involved when I'm presenting these things. If you have questions, ask them in the chat. My wife is looking at the chat. If there are questions, I will. There are no questions at the moment. Okay. So what could be produced? Well, let's talk about the cloud itself. Because we're shooting particles into the sky, particles have to fall. And if the particles are small enough, they are influenced by gravity and air currents, and they will settle slowly over time like snow. So what we get is ash. If products are shot out, say denser, rockier bits that are shot out and can't easily be lifted by the atmosphere, they will fall to the ground, and we call those volcanic bombs. And the term that we use is volcanic bomb because it falls like a bomb would. As that is the scientific term, one of my colleagues got in trouble once coming through security in the airport because she was bringing her samples back from a foreign country. And as English was not her first language, she said, I'm going to be technically accurate at all times because that way, most of the scientific words, their cognates, people will understand. And they said, what do you have in your bag? And she said, volcanic bombs. That was not the right sentence to say. She said, then I had to explain geology to a bunch of TSA agents and security. If there are bigger particles, we call those blocks. And the size, there is a size classification there, but basically head size things, bombs, smaller than that, ash, and there are other words in there. Huge things like the size of smart cars or Volkswagen Beetles, we call those blocks. And they can still follow ballistic trajectories. One of my professors when I was in graduate school was climbing Mount St. Helens after its penultimate 1980 eruption, but when it was still having eruptive activity. And one of his graduate students reported that chunks were still falling out of the sky. Now, not where they were walking, but close enough that they could hear them thud. And at one point, the graduate student said, That one was the size of a Volkswagen. That's not the sentence that you should be uttering when you're talking about things that are raining out of the sky. Were they probably too close? Probably, but we have a tendency of going, danger, danger, like Darkwing Duck, danger is my middle name. So, what happens once the gas is gone? Let's look at those and then we'll look at the really crazy stuff. Once the gas is largely gone, then we get our flat soda. When it erupts, the lava travels much slower. Instead of 4 miles an hour on average, like 10 feet a day, like walking across the room, and that might take a day. And so what we end up getting are a range of different products that showcase that high viscosity. Consider these three images here. In the upper left, this came from Mount Pelée in 1902 in the Caribbean. This moved like a piston, right? Sort of this intermediate, medium gray colored lava moved like a piston. And I tell my students, if you've ever used Easy Cheese, the cheese in the can, right? Cheese in a can. And then you go back to use the Easy Cheese and that hard piston of cheese comes out and sort of flops over. There you go. The picture in the upper right, that's Mount St. Helens. And in 2004, it underwent a period of eruptive activity and built up this lump in the center like a pudding cup thrown onto a plate. And in the background, we have this sort of like curved crater structure. That mound, at the back end of that mound in the center, it's about 400 feet high. In the lower left-hand corner, this is a lava flow in eastern California near the exit for Yosemite, so near Lee Vining. And this is, I think, 200 to 300 feet high because those trees there are colossal. The green that you see there are colossal. And so we have this really tall pile. That lava, instead of being ropey, it's more like the broken up blocky material. My wife and I attempted to climb one of these lava flows in Eastern California. And as the blocks were the size of Volkswagen Beetles and were shifting under our weight, we realized how fundamentally idiotic that was because we didn't want to be crushed. So we did what any sane person would do, which is stand down and just video other people doing it. But it's one of those things. We can see that these form really steep or really tall piles of material because they don't travel very far. They don't spread very easily. So let's compare them. If we have an actual size comparison between shield volcanoes and our stratovolcanoes, what we end up seeing is something which hopefully will pop up in the video feed here in just a second. What we have is a comparison, in this case, put out by the U.S. Geological Survey. Is it appeared? Okay, there we go. Where here we have Mount Rainier near Seattle, Washington, and Mauna Loa, Kilauea, two of the four volcanoes that make up the Big Island of Hawaii. And if you can look at the difference here, Mount Rainier is impressive. It is a tall, conical pile of material. But in comparison, our shield volcanoes are much broader than they are tall, so they look flatter. And that has to do with the viscosity. So, Big Island of Hawaii, is it awesome? Sure. Are there hazards? Sure. Are they bad hazards? Well, no, not really, for property, generally not people. In the case of our explosive things, they tend to be comparatively smaller, but the damage they could inflict is much greater. Recently, just 2 days ago, we passed the 40th anniversary of Mount St. Helens. Mount St. Helens erupted in May 18th of 1980, and it killed 57 people, if I remember correctly. Mount St. Helens is an example of a high viscosity eruption. Here we can see a conical volcano, our stratovolcano, and we can see the eruptive cloud come out. On the left-hand side, we can see some steam because it is white, but most of it is gray. And we can see the cloud, which is going to be raining ash down on eastern Washington, Montana, etc. Idaho. I was trying to think of what states in between. And we can also see something else. The ash can be affected by the prevailing wind direction. The fact that ash is being directed to one side, it's because the wind blows from, in this case, left to right or west to east across America. Right? The 57 people that were killed, some of them were just horribly unlucky. Some of them were at the wrong place at the wrong time. Some of them, this volcano, because it was covered with snow, generated abundant mud flows, and the mud flows charged down valleys and took out roads and bridges, etc. Um, if you want a visual which is somewhat accurate, probably one of the most accurate main budget movies for volcanoes, Dante's Peak. Dante's Peak talks about a hypothetical or fictional volcano in the Cascades of Washington and Oregon, and it's basically looking at an eruption of Mount St. Helens. I think the last image they use as they're rolling the credits is actually a video of Mount St. Helens.
It is not that. So I don't know if they can hear me, but that's CGI, but it is modeled after Mount St. Helens.
Okay. It is CGI, but it's modeled after Mount St. Helens.
Now, the scene where they're flying the helicopter to check the CO2 measurements.
Yes. Okay. I knew they had done something. My wife just informed me that when they're doing the scenes and they're flying in to check the gas measurements, etc., they are using Mount St. Helens. The scene at the end is just a CGI patterned after Mount St. Helens. It's pretty dang good. I've used it to teach, and we actually wrote a paper on the scientific accuracy of it. So let's go in and let's look a little bit more at Mount St. Helens, and we can see some of the problems, and then we'll get into the really crazy stuff for it. I know I keep delaying that, but good things come to those who wait. Mount St. Helens in 1980 produced a very odd eruption. It taught us so much and catapulted geology, and specifically the aspect of volcanology, into the mainstream. Mount St. Helens, when it blew its top, it lost 1,300 feet of height. And so what was left behind was this giant crater, a hole in the side of the volcano. And then periodic eruptions till about 1983 built up a new small cone inside the crater that had been blown up. And then in 2004, we got renewed activity. And what you're seeing is a picture from 2004. The reason why I like this picture is because it shows something about the nature of how these volcanoes how they do. So this volcano, when it blew up, then we get the flat soda that comes out, the lava that is viscous comes out, and it effectively plugs itself because it moves up the tube and then it cools and doesn't travel very far. So it builds a giant pile that ends up covering the hole. Well, that allows more pressure to build up, and then that has to be blown out, and then more pressure to build up and more pressure to build up. Mount St. Helens, if you read some of the papers that have come out over the last 40 years, there is evidence on the backside of the volcano that the volcano underwent a similar explosion, blowing off a large section of its top, because we can find an old scar on the backside, and continued eruptions over, say, the next 50 to 300 years, depending, potentially could build Mount St. Helens back to being a nice cone, but we'd see the scar of the 1980 eruption on its backside. So why does all of that matter? I've delayed the inevitable, and I want to talk about some of the crazy stuff. You can get the ash cloud that goes into the sky and down come particles. You can get the lava flows that ooze out and create these sort of viscous, really slow moving piles. But in between those, we get what we call pyroclastic flows. Pyro, hot, clast, piece. Yes, this is a hot piece. Flows made up of gas and rock that can travel down the volcano at blisteringly fast speeds. So in the upper right-hand corner, what do we have? We have the evidence of a pyroclastic flow. We have these rocks left behind, and notice the light color of them. On the lower left-hand corner, this is Mount Unzen in Japan in 1991, I think it is. In this case, we see this boiling, angry cloud, the cloud rolling in the distance. At the bottom of it would be chugging rocks that are sort of tumbling, somewhat held aloft like an air hockey puck, right? We get this sort of somewhat like an air cushion, which decreases friction, and it travels downward, and it can reach speeds of 60 to 120 miles an hour, maybe even faster. Why does it occur? Because as that material is being launched out of the volcano like a rocket, it needs the interaction with the atmosphere to stir it and keep it moving. If it doesn't have that, gravity wins. And the gravity will take that down, and the material will then have been lifted somewhat above the volcano, And now it falls under the influence of gravity, picking up remarkable speeds. Temperatures 600 Celsius or greater, which is about 1200 Fahrenheit. And that air cushion, if we think about it that way, can help at least some of the finer particles travel over up to 6 miles of open water. One of my favorite bad evidences, bad sciences in recent memory comes from the second Jurassic World movie. When I saw the trailers, I knew I did not want to see the movie because Owen Grady, he's running and the volcano erupts and it is showering both the reddish lava flows and pyroclastic flows. And they generally do not occur together, right? Not even generally at the same volcano. And the pyroclastic flow rolls down and it hits Owen Grady and he disappears in the pyroclastic flow, and you know that he's going to survive. But he can't survive. And if you've ever seen, there's a YouTube channel, Screen Rant does pitch meeting. If you want to laugh, watch their pitch meeting on the second Jurassic World movie, because the guy is pitching to the production studio and he goes, "Oh, so what you're talking about is a pyroclastic flow. So, oh, that's a bold choice to kill off your main character." And he goes, "Oh no, he survives." And he goes, "It would literally boil the flesh from his body." And he goes, "Oh, well, he just jumped into the water." And it doesn't work. We've actually seen evidence of this in 1902. An eruption at Mount Pelée in the Philippines killed a town of 25,000 people, killed the city of St. Pierre, and the number of survivors, immediate survivors, about 6. Long-term, within about a month or 2 of the volcano, it was down to 1 or 2. And one of the girls that survived for 4 weeks, she had been running, and the story was somebody threw her into a lake trying to save her life because the pyroclastic flows were rolling through the town, and it effectively boiled her. She survived, but 4 weeks later, a month later, she succumbed to her injuries.
You have a question?
I have a question.
Yes. The question is, how often, actually, leave it back up. How common are pyroclastic flows during an eruption?
Well, okay, that's a good question. Pyroclastic flows need several factors. They need a high volume of material erupted, and they need an abundant gas, and they need to be intermediate to high silicon content. Not all volcanoes can produce pyroclastic flows. I'm not going to make that bold statement, but depending on the nature of the volcano, pyroclastic flows are a remarkably common phenomenon for intermediate to high silicon eruptions. Now, when I say that remarkably common phenomenon, we have to realize one thing. When a volcano gets to that really viscous nature, they tend to erupt less frequently than our less viscous types. Now, why does that make sense? Because if the lava is easy to move, it doesn't take much pressure, however we define that, to build up to break free. The lava moves with ease. You would expect much more low viscosity eruptions. On Earth, I forget the actual number, but it's something like on Earth, we might have 1 to 4 volcanoes erupting, or at least going through periods of eruptive activity. Usually each year, but pyroclastic flows, they can be common phenomena if we get those viscous eruptions. Now, here's the other thing. Does that always mean that then anytime you live around the volcano, you're going to die from pyroclastic flows? No, because pyroclastic flows, I've heard one descriptor is a pot of rice boiling over. If you think about when something boils over, it doesn't boil over the entire pot at once. What does that mean? That means from one eruption, they might not go all directions. Pyroclastic flows, because they have that dense rocky bottom, that tends to make the pyroclastic flows follow valleys, path of least resistance. Now, the problem with it is if it makes an abrupt bend, the cloud that's on top can go, "Oh, I'm not going that direction," and keep going forward. So we know that even though pyroclastic flows can be common, especially around certain volcanoes, we know that they generally follow valleys and move into low spots. So that increases our ability to devise hazard maps, et cetera, to go, don't live here, don't build here. In the event of increased activity, these would be the places you'd want to evacuate first. Does that answer the question?
Yeah, I think it does.
If it does not, I will go back. That's a good question, though. Uh,
And the number of estimated eruptions per year is between 50 and 80.
okay, hey, I was conservative.
It depends on, whether, because the problem is a lot of volcanic eruptions we don't see.
Yes, my wife said doing a quick search because I just don't know the number off the top of my head. The number of eruptions each year could be 50 to 80. Some of the eruptions occur in out of the way places where nobody lives. So we might not see them. We might be able to detect them via satellite, but not actually have ground truthing, or they're on the ocean floor. And that takes into account all eruptions, viscous and low viscosity. And I would imagine if we did the analysis for that, the vast majority of those would be low viscosity eruptions. You could also look at it this way, and this is something from a probability standpoint. And this is another way of looking at it. Minor events are much more frequent than major events. You are more likely to stub your toe than death by asteroid, right? So if we look at a volcanic eruption, just saying that a volcanic eruption occurs doesn't say anything about the magnitude of it. So as magnitude increases, probability decreases. So what is the likelihood of a major eruption? All of that just saying this number of eruptions. So most of those are minor. Most of those are also low viscosity. So we can have a low probability of these occurring, but when they do occur, man, you don't want to be nearby. I know I got to go to Reventador in Ecuador, and I got to go 3 months, I think it was, after it had erupted, 2 months after after it had erupted. And it's in the cloud forest, which means you have to hike through the jungle. That's a story for another day because that was miserable. When I hiked through the jungle, you eventually got to a point where the pyroclastic flow would come down and it buzzed off the jungle, removed the jungle, like somebody just taken a razor on a beard, just gone. And it was like a knife edge because as that came through, it just wiped out and it showed the raw power. That hurt nobody. It damaged the national oil pipeline of Ecuador, but it didn't kill anybody because it was remote. It was in the jungle. I hope that answers the question. I hope I didn't belabor the point there. The one tamale that my students always ask me is this: well, what about Yellowstone? And Yellowstone is an interesting animal because we have so many misconceptions about Yellowstone. So many misconceptions that people can create panic when there is absolutely no panic. So, Yellowstone sits in the northwest corner of Washington state, and it is what we call a super volcano. I always liked the term super volcano because it makes it sound good. I understand super is just a descriptor of big things or powerful things, but when we have Superman, super good, and then we have super volcano, ooh, I want that. We have this idea that if Yellowstone erupts, it'll be apocalyptic, as in it erupts and US is gone or functionally gone. That's not the case. It would be bad, but it wouldn't be that bad. And here's the reason why. Yellowstone has never been associated with a major extinction event. We don't have this like, oh, there were the dinosaurs and then bang, and they're gone. Why? A, it was more recent than that for my geology folks in the crowd. It was the earliest eruption from Yellowstone or that area was about 16.5 million years ago, and the dinosaurs are older. But let's even say, okay, the crazy like giant mammals. No, we don't see this massive die off and then the eruption stops. We don't have that. It would be regionally bad, but it would not be apocalyptic. And I will qualify that. My wife goes, and I'm gonna qualify that here in a minute. So, what is Yellowstone and how does it differ from the other eruptions we're talking about? Well, this gets into a little bit of plate tectonics. The Earth's surface is broken up into 6 to 10 major plates and a bunch of smaller plates. But imagine an eggshell that is cracked and the pieces move like puzzle pieces, but they're curved and they move around the Earth and they interact. As they bump and they grind, we get earthquakes and tsunami and volcanoes and mountains, etc. Under the Earth, we think that those are driven by a complex series of convection currents, in other words, like stirring in a pot of soup, and that allows them to move across the surface. We could spend an entire lecture talking about plate tectonics, and my students would chuckle and say, one lecture, you usually take 4, right? Because I like to bloviate. So if we if we have this, there is something else that goes on because Hawaii and Yellowstone and a bunch of others of these, they don't jive with that model because they don't sit at the boundaries of the plate. So the puzzle pieces rub against each other in some way or move apart. They're in the middle of plates. And so there has to be some other process. And what we think is near the base, we have 4 layers of the earth: crust, mantle, outer core, inner core. At the base of the mantle, we get this weird varied zone which creates periodic blobs of magma, big blobs that rise. And the visual we have, sort of like a lava lamp, they rise toward the surface. And when they get under those puzzle pieces, they can burn through like a blowtorch and create a massive volcano at the surface. We think that's how Hawaii formed. Hawaii is not on a boundary of a plate. It is in the middle of a plate, and we think a blowtorch has created the big island of Hawaii. And if you look, the other Hawaiian islands are in a line, and what happens is that blowtorch sits underneath, creates a volcano, plate moves, new volcanoes created, plate moves, new volcanoes. And so what do we get? This string of pearls, right? We get the islands. The material that's produced, low viscosity. Well, what happens if that occurs under the continent, for example? There we get this high viscosity magma, which is generated nearer the surface. And so we get a vast balloon of high viscosity magma that when it erupts, it needs an incredible amount of pressure to erupt. So what are you looking at here? The 5 numbers here show what we think the development of a Yellowstone-like supervolcano looks like. The material, the magma underground, has been colored black for contrast. It is actually, remember, when the products are produced, it should be intermediate gray to a light gray in color, but it's just colored black there for contrast. We get a whole bunch of cracks, and you see, okay, it undergoes a major eruption. Well, the model that we have is probably something like this. If we would look at it from above, you'd see this sort of like, not necessarily concentric, you might not be able to see all the rings, but sort of a ring of volcanoes, ones that in and of their own right would be impressive, scattered around an area, suggesting that magma is moving up and periodically throwing out material in smaller eruptions. But if we build up an incredible amount of pressure, those start erupting, and as they erupt, more and more magma is tapped, and more magma wants to erupt as lava, and then it just gets bigger and bigger and bigger, almost like positive feedback. And when it does, we can get a runaway eruption that is not just one single 2012 movie style eruption, it's actually many building up to a big eruption. Like stampede of cattle, right? We get the one that's spooked, and then more spooked, and then suddenly the entire herd moves. When that material erupts, now we get a void, an empty space created under the surface that makes the surface gravitationally unstable, and it sinks in, and we get what is called a caldera, which comes from the word for cauldron or big pot. And if you look at that last image there, 5, that is basically what modern day Yellowstone National Park looks like. The park is largely built, I think 65% of the park is built on the floor of the old volcano, sort of in the mouth of this cauldron. We know that there's still heat in the system because we get Old Faithful, or because of earthquakes, she's, I guess, semi-faithful, and we get paint pots and all these mud pots and all these other things, the thermal features. So we know there's still heat in the system, but people go, when is it going to erupt? And the way that they ask that question is almost like they want it to, because they want to see the spectacle. So let's talk about what it would look like. In that big white space, here in a moment will appear a series of circles or ovoids, I guess ovals, looking at ash distribution from Yellowstone, from Mount St. Helens, multiple different eruptions of Yellowstone, and a similar Yellowstone-like caldera in Eastern California, which we call Long Valley Caldera. The most recent eruption of Yellowstone happens... Okay. The most recent major eruption, and I use that term specifically, major eruption of Yellowstone happened about 630,000 years ago. And that is that light gray blob, which you can see that we have record of ash from Yellowstone in Texas and in Louisiana, Arkansas, Minnesota, or Missouri, Wisconsin, etc. Right? The darker colored circle there is a 2 million year old eruption of Yellowstone. It has erupted generally in its current area. It's erupted 3 times in the last 2 million years, and we've shown 2 of those here. And we call that super because the sheer scale of it. And then we see Long Valley in the lightest gray there. It also covered a huge section of America. So we go, well, how could that not cause a mass extinction? Well, in the fossil record, we don't have evidence of a mass extinction from that. However, and this is the caveat, we're doing a test now. We have a technologically connected society, which is agriculturally based, at least the backbone of it is agriculturally based, next to or at least in the damage area of the volcanic eruption. For example, in all 3 of those cases, Long Valley and the 2 Yellowstone eruptions, what was affected? The Central Valley of California, a quarter of the nation's food and 1% of the nation's land. What was also affected in all 3 of those cases, to a lesser extent, Long Valley, the Great Plains area where we have a large section of our food production. So, would it cause a mass extinction event? No. Would it cause a major hit to American food production? Absolutely. And then all of the domino effects that would occur in our society as a result. Would it interfere with electronics? Absolutely. Ash in the sky. Would it affect global climate? Absolutely. Because short term, ash in the sky and particles in the sky would actually act temporarily to increase heat as heat was trapped, but long term would act as a screen which would diminish warming effects of the sun, and the influence of that could last potentially up to 8 years. Now, it would diminish with time, the influence would diminish with time, so that could lead to famine because our society is dependent on going to the store and being able to buy apples from New Zealand in no matter what season, right? Or whatever. Now, here's the thing. When people ask this question, well, how often does Yellowstone erupt? That's actually a dangerous question because the most recent eruption of Yellowstone was actually 3,500 years ago, but it was a comparatively minor eruption, something on the scale of, say, what happened with Mount St. Helens. When people ask about eruptions of Yellowstone, they want the big ones. They want this, what looks apocalyptic. And a couple of years ago, I don't know if you saw this, and this is funny. A couple of years ago, I'm telling you, it's funny. A couple of years ago, a news article came out that said the government knows something that we do not. Animals are leaving Yellowstone in droves, and they showed videos attached to it of buffalo leaving Yellowstone in wintertime. And they said everybody knows that animals know things that we don't. So obviously, the volcano is doing something that we don't know. And the National Park Service had to get involved, and they said, you realize it's wintertime? Do you know why the buffalo are leaving Yellowstone in herds in wintertime? Because they need to eat. They need to find food. They said it's not some grand conspiracy. It's called migration, right? And then about a week later, not to be outdone, they said, and this is, if you're going to try and do a conspiracy, you always want to wrap it in good science and then at the last moment, switch it into the crappy science, because that way, good, wait. And they said, a seismograph is a device which can record earthquakes. As magma moves onto the ground, it can break rock, which can be recorded on seismographs. True. So if Yellowstone were having magma moving onto the ground, we should be able to see it on seismographs. True. So then they showed the one seismograph that was just going crazy, like just saturating the printout. And we go, oh my God, something's going on. Yellowstone, the National Park Service said, we have like 150 sensors around Yellowstone. 149 of them are quiet. One of them is going crazy. Something tells me if something is this apocalyptic, if you are the only person in a crowd claiming that you have knowledge and something apocalyptic is happening, it's probably not happening. And they said, let's go out and see. And they go, oh, look, a faulty wire. And they replaced the wire and quiet. But it was almost like either we wanted to make money off of the fear, or we were all like, could it erupt? I kind of want to see that, even though I don't. So let's talk about a matter of scale. when we talk about volcanic materials, you'll hear numbers like this. If that volcano erupted, it would fill a football stadium to a depth of 3,000 miles or something crazy like that. Something that the human mind has trouble understanding because we don't generally fill our football stadiums to even 1 mile, let alone 3,000 or whatever it is. So in geology, we have, because we're dealing with large scale processes, we have created we have used, we don't create, in this case, we've used the volume of 1 cubic kilometer as a good measuring stick. Well, what is a kilometer? About 3,000 feet in the side. So a cube that's 3,000 feet in the side. And if you have trouble visualizing that, imagine a cube about this big, and you'll see my hands here in a moment. A cube about this big, and for scale, the Eiffel Tower would be about this big. So it's a big object. If we look at the volcanoes and we try and compare them by their products, Mount St. Helens, which was considered a medium-sized eruption, had 0.3 cubic kilometers of new material produced. Much of the rest of it was just the volcano failing and sliding downhill. Okay. Total with that, with the chunk that was actually lost from the volcano, we had 3 cubic kilometers of material, but most of that was just the volcano broke up and slid down. Mount Pinatubo, that nuclear-like explosion I showed you at the beginning of this, that was 7 cubic kilometers of material. And I put here for scale, Mount St. Helens, 57 dead, Mount Pinatubo, 1,200 dead. That number actually downplays it a little bit because the effects lingered, mud flows lingered. In 1883, we had Krakatoa volcano erupt. The eruption, the physical explosion, the pressure wave generated by the volcano was able to be recorded going around the globe about 7 times, diminishing in intensity. It rattled windows 3,000 miles away. It was a colossal explosion. 37,000 dead, mostly from pyroclastic flows and tsunami. If you've been to Oregon, we have Crater Lake in Oregon, 75 cubic kilometers. This starts getting us into the supervolcano range, but usually these are listed as large, right? We've gone into large. And that's whenever you hear somebody say that, what is, if they come up with an adjective like big or hot or large, well, what does that mean in comparison to what? In 1815, we had a volcanic eruption called Tambora, and Tambora volcano is in Indonesia. It created what historians have referred to as the year without a summer because it affected global climate enough that it interfered with the growing season, caused food die-offs. We reported ice in the Gulf of Mexico, which generally we don't do that, right? And some numbers will come up here on the screen in a moment. 71,000-ish died from Tambora, and that was largely tsunami and pyroclastic flows, largely tsunami. All right, because why? Pyroclastic flows hit the water, and volcanic eruption actually broke the volcano up into pieces. And as the pieces hit the water, we disturbed an incredible amount of water. But look at those last 3 for Yellowstone: 0.6 million years, 1.3 million years, 2 million years ago. These huge volumes of material. So what would happen if the volcano erupted today? Again, we lose much of our food. That would cause global famine. And then we would run into a situation that people would die. The estimates are hard to know because we have a technologically advanced society, but how would we respond with panic? Probably something on the order of 1 million dead, maybe more, probably more, but it's hard to estimate. And some of those would be immediate deaths because the people that experience it the worst would be people living in Wyoming and in Idaho and in Western Montana and in Utah. So Salt Lake City, Boise, etc. What would it affect global climate? Well, that's hard to tell. We can't just do, and I've done it here, but we can't just do a linear change, volume to temperature, because it doesn't work that way. It's not just a direct linear change, but let's even say 15 degrees. That would be a very severe. And we go, well, 15 degrees is not bad. Yes, but that's an average over the planet. If we just sort of like took all of the highs and lows that were shifted and we go, well, we just reduce those by 15 degrees, that would be considerable. It probably won't get that extreme. It is hard to estimate what the temperature would be. But again, we haven't had mass extinctions in the past. We are doing a test now. So what have we talked about? We talked about the low viscosity stuff. Don't be stupid. Don't be unlucky. They generally follow valleys and low spots. Even the eruptions that shoot up into the sky, as long as you're not right next to them, you're fine. Once we start getting into the high viscosity stuff, then we start getting into explosives. You don't want to be nearby. It's not the lava that kills you, it's the ash, pyroclastic flows. And then if we get into the incredibly super, like changing the paradigm that creates the volcano, then we get into Yellowstone. I'm going to leave you with two last thoughts and then answer questions. I should have covered this at the moment, but think about the volcanic ash itself. Fundamentally, that's a breathing hazard because particles in the lungs, they're basically little tiny glass shards. They destroy the lungs, right? Or at least severely damage the lungs. And silicosis, there's actually a much longer word, but we simplify it to silicosis, is breathing ash into the lungs. But think about it another way. Cars have air filters. A lot of air conditioners, et cetera, they have air filters. That affects technology because now it clogs up air filters. It also affects airline travel because airplanes are just large vehicles with big air filters. And we've had incidences where we've had planes that have their engines have cut out because they got caught in a volcanic eruption. Ash comes sucking in. Why? Because even if you've watched the movie 2012, airplanes are not as maneuverable as the way that they show them, especially commercial aircraft. They don't just, they can't do that. So we've run into situations. You should look up a flight coming out of Indonesia, British Airways flight coming out of Indonesia in the early 80s. They got caught in a volcanic eruption cloud, shut off all four engines, and they had to turn the plane into a glider because otherwise it would have plummeted. So they kept the nose up, they turned it into a glider, and I think they had to glide for 30 miles unpowered, something like that. And then when they landed, the sandblasting effect on the front window, they basically had to, they didn't, but they had such a limited visibility on the sides that were unsandblasted. For all intents and purposes, they had to stick their head out the window in order to land the plane. So are there questions? Any questions floating around? If anybody has any questions, ask me. That is the end of my presentation. I figured I would cover some of the misconceptions that we have about volcanic eruptions, and I could tell you crazy stories about climbing volcanoes. That's sort of not what this thing was about, but if you're interested, I could do that.
No questions yet. Maybe give people a chance to respond.
Okay, I'll give.
Okay, it cracked out there for a minute. I don't know. You do a short story about a volcano.
Okay, I'll give you a short story about a volcano because I think it's funny. I have been to Ecuador, Peru, Italy, and then the rest of my volcanoes have been in California, studying old volcanoes, California. I've been to Yellowstone, etc. Ecuador has some of the most volcanoes on planet Earth, and the volcanoes break up into four belts from the southern to the northern end. They basically break up into four lines of volcanoes. So you can be in Ecuador and be not far from a volcano. We attempted to climb Cotopaxi volcano, which is a dormant volcano. I forget the exact elevation. The elevation of the top is something like 18,000 feet. Cotopaxi, yes. And I came from Buffalo, New York, right? For doing all my travels. And being in Buffalo, New York, we tended to fly out in wintertime because since the seasons are reversed, we fly out in wintertime and like snowbirds, we do our research then when it's warmer in South America.
Almost
5,900 meters, 6,000, 18,000, okay, almost 20,000 feet. Buffalo, New York is 700 feet-ish above sea level. So functionally, we treat it as at sea level. And if you've ever been to a higher elevation, like you've gone to Denver, for example, or you've hiked a high mountain, you feel out of breath, that's the beginnings of altitude sickness, right? Your body, if you are used to a lower elevation and you want to climb up to a higher elevation, you have to do that slowly. You have to give your body time to acclimate because down at a lower elevation, there's more oxygen for you to breathe. And I don't know why I still have this on. We'll go back to stopping screen share. Because that way I'm not just this little tiny guy in the corner. Yeah, I can have a more of a disorganized room. This is what a geologist's room looks like. Uh, if we have that, when we were climbing that, if we're climbing a volcano or climbing a mountain, we have to give our body time to acclimate because your body is used to a certain amount of oxygen as you breathe in, and your body needs that oxygen for processing wastes, etc., right? All of your body processes. If you get deprived of oxygen, then your organs start shutting down. You start getting your brain starts getting fuzzy. It's hard to think. You start having to try and breathe faster in order to get enough oxygen. Well, I stayed in Peru for 2.5 months on volcanoes, and even though I was eating a lot, I ended up losing 19 pounds because my body just burned off so much energy breathing more because I then have to work harder. When I got back, my parents was like, "Are you okay? What do you need?" And I went Arby's, right? Something that was fattening. So we leave Buffalo, New York, 700 feet above sea level. We fly down to Quito, and Quito is 10,000 feet above sea level. What we should have done is stay there for several days, do minimal activity, walk around, see the sights, relax. Because we're on a federal grant, we didn't have time for that. So we flew down, we stayed one night in Quito just because of the timing. We drive down to the base of Cotopaxi the next day, which is about 7,000 feet above sea level, 10 times the height of Buffalo. We eat dinner, and I'm feeling tired. You can drive onto the volcano. You can drive up to about 14,500 feet. And there's a little parking area there. And it is terrifying to see buses navigate the labyrinth switchbacks coming down Cotopaxi. And you realize if their brakes fail, they're just in serious trouble. So we get to the parking area, and I'm tired because my body can't get used to not having enough oxygen. So we hike, and we hike up 1,200 feet up the volcano, whatever it is, to the refuge there. For people that want to summit the volcano, they have to stay there overnight. So we hike up to the refuge, and all the way, because there's glaciers at the top, ice is pelting us. Wind is blowing ice and grit into our faces. And that's one of my first times ever on a volcano. So instead of bringing like ski glasses or something like that, I brought my high school biology little safety glasses, right, for like the biology lab, and they're getting pelted with ice. And we get up to the refuge and we sit down and we go, okay, we're going to take a minute. Then we're going to hike up farther to collect some samples because that's what we came for. And I said, I can't go up. My advisor's there, what other graduate students there. I said, I just can't walk up any higher. And the professor looks at me like I'm a prima donna. Is like, this is the reason why we came. We're hiking. I said, I can't. I physically can't. So he goes up, and I pass out. Complete fundamental unconsciousness, bam, down on the table. I don't realize this because it happened gradually. I just passed out on the table. And I got awakened by a German tourist, and he said something to me. I have no idea what he said, but it was evident. "Are you okay?" was his statement. And I looked up in that comic way, like you just wake up and you have like the lake of like, you know what I'm talking about, around you, right? And I'm like, I'm not okay. And about that time, he says, "Just sit here." And I'm like, "Well, I can't go anywhere, right? My ride is gone." So I'm sitting at the refuge. My advisor comes down. Now he's bushed. So he comes down with this graduate student. They go, "Okay, that was hard. We're going to sit here for a moment." I said, "I need to leave right now." And my advisor gives me that look like, you don't dictate what this trip does. And then he looks at me, and I am Shrek green. And he goes, "Oh, we need to go." So we go out the back, and I just lose it because my body was going through toxicity. I could have died. It's not something like, okay, well, they say just go down an elevation and you'll be fine. That can work. But if the damage is already done, the toxicity buildup just gone. But we also learned something else about being at high elevation. Uh, be careful if you have a beer and you're not used to being at or high elevation. Your body does not know how to process that. It doesn't process it at the same rate. So you can have one beer and be dancing on a table with a lampshade on your head because your body can't process it effectively. Uh, Now, if you can develop a tolerance at higher elevation and acclimate, you can school people when you come down to lower elevation because your body so much more efficiently processes it. So you can drink more. And we see actually athletes do this. Athletes will do this. They call it natural doping. So it's rather than taking drugs or all these things. Hello, my wife is in the background. If you go to higher elevation, uh, your body then gets used to dealing with less oxygen in the blood. If you then come down to lower elevation, say your tournament, your race that you're running is at a lower elevation, if you come down close in time to the start of that race, on the order of several days ahead of that race, your body, it takes time for you to lose the acclimation that you've gotten. So your body is now able to deal with less. At lower elevation, there's more oxygen. So your body's just suffused with it. It goes, I don't need all this, but by God, I'm going to use it. So you can run harder, longer. So playing around with that, I had a story, one of,
Well, hey, before you launch into another story,
yes.
you actually have some questions.
Oh, good questions.
Okay.
Otherwise, I'll just tell stories forever.
You will.
I will tell stories
Don't give
forever.
him the opportunity.
I'm nearly 40, but I've already got the old man syndrome.
What's your favorite volcano?
What is my, what is my,
I guess maybe I'll ask.
no. My favorite volcano has to be Reventador volcano in Ecuador.
Wait, seriously?
Yes,
Why?
because it was the most miserable experience I've ever had on a volcano. And I realized if I could get over that, I could do anything. Because hiking in a jungle that is actively raining, that farmers are actively grazing cattle on, which means now there are pools of water that are pestilential. And we were told by the conference organizers to wear galoshes rather than, I had like 10-inch all leather combat boots. And they go, those wouldn't be good, but now you have to wear galoshes. So my foot is sliding around inside and it comes off in the mud. And I'm stepping into the mud. My one of my colleagues, the people that I worked with there, they were like, well, he's done. He's never going to do this again. And one of my colleagues got to work with those people later on. And somehow my name came up in conversation. And they said, so did he quit studying volcanoes? And they went, nope, he's still doing it. He's in Peru right now on volcanoes. And they went, why? He had such a miserable experience. I'm like, because I learned, right? I went, thank you, sir. Can I get another?
Another question.
Sure.
Let's see.
Remember, always do what you love. But if you can't do what you love, figure out a way to turn that thing into a. Okay.
Here, the next question is how do volcanoes in the ocean floor differ from ones on land?
Ones on the ocean floor different from ones on land. Okay, so an interesting thing happens with volcanoes underwater. If the volcano erupts into shallow water, and there is a number, and I don't remember what the number is off the top of my head. If the volcano erupts into shallow water, it tends to be mildly explosive because you're getting, the scientific term is fuel coolant interaction, like grease, water, bad, right? In the case of lava, when the lava enters a shallow body of water, what happens is the lava heats up the water, gas can be produced, and as the gas expands, steam expands, it goes through a tremendous expansion. You can get explosions because as it expands, it can fracture the lava more, exposing more water, more steam, and so you get these explosions. If it is under a deep depth, a significant depth of water, deep depth, sure, the gas can't easily escape, and the water, which is tremendous at being able to insulate from high extreme temperature changes, can cool it off. And what we get is this strange surface which can become really hard and cool off almost instantly. And what it will look like is a toothpaste tube, a hard outer shell with still liquid lava in between, right? And we call those pillow lavas. And the reason why we call those pillow lavas is because if that lava in that tube is still liquid and still has pressure, it can break through the surface and it oozes out like toothpaste out of a toothpaste tube, cools again, the process repeats. So instead of getting tremendous explosions, we get these oozing blobs that will erupt out. And this goes back to something like if you've ever left the cap off of the toothpaste tube. When you leave the cap off, the toothpaste right in the entrance of the tube starts to dry out. And then when you push it, it has to push that out of the way. And then fresh lava or fresh toothpaste comes out. Same logic. We can get one other type, which is awesome. We have these things on the ocean floor called black smokers. And black smokers look like a fire on the ocean floor with a big plume of what looks like smoke coming out of it. And that's because water moves down into the ocean floor under cracks. And even though the lava is not exposed, we have magma under the surface, right? lava above surface, magma below surface. If the water gets close to the magma, it can be heated. Hot water wants to expand, wants to rise. So it rises back through other cracks and comes back toward the ocean floor. Hot water under pressure can dissolve an incredible amount of stuff in it. Obviously, it can dissolve salt, but it can also dissolve things like metals, gold, silver, platinum, tin, iron. And what we find is these black smokers are largely iron and then a whole bunch of acids, iron and then some of the other precious metals in much smaller concentrations. They're carried back to the ocean floor. They interact with the much colder water of the ocean floor, and the water goes, remember all that stuff that I had dissolved? I can't dissolve it anymore. And it appears as a precipitation. And so we get these clouds of iron, precious metals and acids on the ocean floor. And the cool thing is that can actually set up restrictive, localized ecosystems, like a whole bunch of people huddling around one thing in a cold environment. So we get these weird ecosystems that have developed there. That one actually, it makes sense that they would occur, but it was one of those things that we didn't expect. The ocean floor in general, there are currents that move down in the ocean, but we know that water is really hard to change its temperature. The water at the bottom of the ocean floor tends to be really cold, almost uniformly cold, around 4 degrees Celsius, 3.5 to 4 degrees Celsius. And the variations there are largely due to big ocean changes like the pot being stirred. But when we were going around on the floor of the ocean, we had a temperature gauge on the outside of one of our vessels, and it was recording 3.5, 3.7, 4, 4.1. It would vary back and forth. And then suddenly 20 and 40. And we went, what's going on? Flip on the headlights and see these black smokers. Let's see. It is weird seeing yourself on time delay because it looks like caca, caca as I'm raising my arms because I've lost the context. Any other questions? If there are no more questions, thank you all for joining us, Blackland Geology and Reptiles. We will be doing some other talk next Friday, and it could be her, it could be me. We haven't decided exactly what. If you have anything geologic that you would want us to talk about or anything with reptiles, I can give you a lot of information. Plate tectonics. We could do severe weather. We could do climate change.
Severe weather would be more practical.
Severe weather would be more practical. And I wouldn't get as many death threats. It's true. We could also, if you would be interested, now I wouldn't easily be able to talk about coronavirus, but we could do infectious diseases as well, because I have taught about that for natural disasters. We could do Spanish flu, we could do bubonic plague, I could talk about infectious diseases and treatments in general, and how far we've come and how that has been recent. The treatments that we attempted to give to George Washington, and then when we look back at them just 250 years later and we go, by God, that was barbaric. And then we could talk about, I think, Louis XIV with all of his enemas that he used for health. Other questions? I know, it's 10-second delay. Language. Okay. Then coming here from an undisclosed location somewhere on the geosphere, Black. Yes. All you know is in the background we have a cat and sunlight coming through. If there's anything, put it in the comments. Otherwise, we'll pick back up here next Friday, 5 p.m. Central Time, some other topic. Thank you all for coming. And if you know people that would love the chance to have somebody else teach their kids, right? I know that we're all going, I never had much hair to begin with, but I know that some people that had a lot are pulling it out now. If you are interested, if you know somebody, we have pricing on there because we can give lectures. We could do long distance birthday parties with snakes, etc. If you have anybody who has an interest in this, and I can teach, we can both teach from small kids to adults. Okay, because sometimes somehow we all act the same, right? Have a good night, and we will see you next Friday.